Now we want to think about the situation where the aluminum strip is above the magnet. Remember, the aluminum strip is in this direction, current flowing in this direction or this direction, either one direction or another along the strip. Magnet down here exerting a magnetic field or creating a magnetic field that's either directly up or directly down. And when we put a current through it, resulting in a flow of charge either in this direction or this direction, the aluminum strip is deflected either this direction or this direction, perpendicular to both the line of the current and the vertical direction of the magnetic field. So, the force exerted by a current I moving in a length increment delta L is just going to be I delta L cross B. The I delta L will be either in this direction or this direction in the example we're talking about. The B either up or down, so the cross product is either this way or this way. Equivalent to an I delta L, we could have a QV. So the force could be QV cross B. This is the force experienced by a charge Q moving at velocity V in magnetic field B. The units associated with this, and incidentally, this is probably maybe the simplest of all these relationships because everything is right there. There's nothing more to do. Now it gets a little more complicated if you don't have a straight line path or a constant magnetic field. In that case, you do have to do an integral of the I delta L cross B, and it'd actually be I dl cross B in order to figure out the force on the current carrier. Okay, but it's a fairly simple relationship. This and this are simple enough relationships. Now the units, the force is going to be in units of Newton, magnetic field in units of Tesla, charge in units of coulombs, velocity in meters per second. It follows immediately that Coulomb times a meter per second times a Tesla has to be a unit of a Newton, and that the Newton therefore, or the Tesla therefore, has units of Newton seconds divided by Coulomb meters. So there's our unit of Tesla plugged into either of these equations. If you have the correct units for the other quantities, the SI units, you're going to get a force in newtons. Now, of course, the calculation of the force on, let's say, a loop of current is going to require either a line integral or an argument very similar to that of a line integral. And in applying this, we would find that that a magnetic field, a constant magnetic field, will tend to produce a torque on a loop, a square or a round loop, for the magnetic field has certain directions with respect to the loop, and that gets a little more complicated. This is a basis for that, for the interaction of a loop with a magnetic field. The idea of magnetic moment and so forth arises directly out of this. So we have a very simple law that leads to some fairly complicated integrals and some fairly deep analysis.